Now, distance in kilometres of a cyclist from his home after t hours is given by this function here. Now, what type of function is this, just out of interest? Can you tell me what type of function is it? Cubic. So it's going to have a maximum and a minimum, alright? So, when it has its maximum and minimum, what's going to happen is it's either going to go this way, something like that. So what's going to happen is you're actually going to go further away from home. So if I just was to just draw this in red, you're going further away from home because your slope is positive. Do you understand? A positive slope here means you're going further away from home. A negative slope in this context, you're coming closer, right? So now you're coming closer to home. And now you're at your minimum point, your minimum turning point, which is the closest you get to home. And then all of a sudden you're going away from home again. Or something like that. Now the great thing, sorry. So just put all that in, but instead of using S, what do we use? F of x, and instead of t, we're going to use x, because that's the way our calculator is programmed. Okay, so we just use minus 3 x squared plus 3x plus 4. Okay, just go on. Just what? There we go. Now, plus 4, thank you. Now, should I start with a negative number?
Yes.
No, what does x stand for again? X stands for t, and t stands for? Time. So you can't have minus time, so what's a good start off point? 0. Okay, let's go 20 seconds in the future, okay? And one second at a time. So here's what happens. You start 4 kilometers. You start 4 kilometers away from home. 0, 4. After 3 seconds, or 3 hours, after 3 hours you're 13 kilometers away from home. After 4, you're 32, 5, 69, 6, 130, 7, 2, 2, 1, 8, 3, 4, 8. So you don't seem to be getting close to the home at all, do you? No. Okay. So
Is it wrong then?
no, not necessarily wrong.
Oh.
So this
There are 4 there.
so this function seems to be increasing all the time. So although it's a cubic function, imagine I did this instead. Just take that part out for a second. Imagine I did that. I moved the cubic function so that it's always arcing upwards, and the maximum and minimum actually occur with negative time. So we're modelling this on an equation where we're just constantly getting further and further and further away from home. Does that make sense? All we did was shifted the curve across. So the maximum and minimum are probably located in a different in the negative x way. So it doesn't exist in this question. So we're only concerned about the positive part. I think, yeah.
Remember, yesterday's shows one didn't actually have like a maximum minimum.
Yeah, it could be like that as well. Yeah. The honest truth is I wouldn't know without doing a bit of calculus on what's what. Now, what we're going to just do is analyse the question now. How far did the cyclist travel? How far the cyclist from his home at the very beginning? And you're just going to get S equals 4. The SDT, guys?
3t squared.
Now, 3t squared, yeah? Minus 6t plus 3. Remember I said it always seems, the slope always seems to be positive here, doesn't it?
Yes.
Because you're getting further and further and further away from home every time. So, if I was asked something like the last question, now the last question says prove that it's always increasing. Imagine, like, what could I do here? What could I take out? 3, couldn't I?
Yeah.
And I'd be left with t squared minus 2t plus, yeah? And what happens if I factorise? That's not 11, that's not 11, that's a bracket. Now what happens if I factorise what's in here?
Get that.
I'll get t minus 1 bracket, which just so happens to be a square. 3 bracket t minus 1 squared. What can you tell me about that slope?
Always positive.
Always positive.
Yeah.
3 times the perfect square is always. So the slope is always positive, which means you're always cycling away from
Oh.
home.
So he's not coming home.
Well, he's not coming home on his bike. Gets a new type of motion. Okay? So that coincides with what we learned here, wasn't it?
Yeah.
That we're always going away from home, therefore the slope is always increasing.
So,
Now, this, by the way, if you didn't actually ask you this is just using the last exercise to explain this in context, okay? Now, you're asked a much simpler version of what's going on. Hence or otherwise, find the slope of the cyclist at t equals 3. So what do I need to do with this formula here? Anywhere I see t, put in 3. Now, we're missing one thing here, right? If s is the distance formula, the first derivative, which is the slope, yeah? The slope in this context is the speed. The second derivative is the what usually is associated with speed. And something else. Acceleration. First derivative is speed. Second derivative is acceleration. Okay. So this question, we're basically want to find out the speed when our time is equal to 3. So replace all t's with 3's. Now you don't put it in the original equation because the original equation is referring to distance. The differentiate equation refers to speed. So it's 3 times, what's t is 3 squared, minus 6 times 3 plus 3. And what you get?
12.
18.
12.
Oh sorry, yeah, 20, yeah you're right. You get 12 when you put that in the calculator. So 12 what though? Kilometers per hour. You knew that because it says kilometers and it says hours. Find the value of t when the cyclist is momentarily stopped, and how far is the cyclist from his home at this point? When do you stop? When your speed is 0. Speed in this type of question is which derivative? The first or the second? First derivative. You want to find out where the first derivative turn into 0. So when is your slope 0? When do you bottom out for a second? When do you stop moving? Slope means you're moving. Okay, so slope is speed in this question. So solve that equation. Am I allowed to divide both sides by 3 this time?
Yeah.
Why? It's a solve question. Now t squared minus 2t plus 1. We actually already solved this earlier, didn't we? T minus 1 and t minus 1, t equals 1. Now the next thing they're asking is, how far from home are you at this point? How do I find that out?
Put 1 in for t.
On which equation though?
The first one.
The very first one gives you distance.
Yeah.
So you replace 1 for t, so you get 1 cubed minus 3 times 1 squared plus 3 times 1 plus 4. But as it turns out, we already know it. After 1 second, when your speed temporarily stops, you're 5 meters away from home. So 5 meters away.
no, 5
But see what like
Sorry? 12 by 20
yeah.
is
So
240.
if you go back into the calculator,
Yeah.
20 hours he's at like 6,000 miles an hour.
Yeah, it's too fast. So what you'd say, Cameron made a really good point. Now Cameron, that type of question gets asked a lot. When does the model fail? Is what you could be asked. And you're dead right. I'd argue that if this is a cyclist, yeah? Okay, so look at this. He travels 1 kilometre in the first hour. He travels roughly 10 kilometres in the second, that's doable. 18 in the third is doable. Now you're getting a bit. 37 in the fourth, professional Tour de France cyclist can do that. And then 70 kilometres an hour.
After 6 hours.
After 6 hours, the model is becoming unrealistic, and especially 7 to 8, doing 120 kilometres an hour on a bike is unrealistic. So you say, you could argue that this model, this mathematical model in question, only applies for hours 1 to 5. And that's a really good thing to do. Yeah, that's really good sites there. Let's yeah, this is a really quick one. Let you guys